So here we go. So you know what's the magnitude of I? It's a unit vector. So what is it? 1. And vector A is equal to A1, comma, A2, comma, A3. So if you dotted that by 1, 0, 0, what happens to A2 and A3? They go away, so you're left with just A1. So you can do that for B, and you can do that for gamma too. Beta, cosine beta, and cosine gamma. What about this right here? Cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. Why do we know that that's true? Why do we know that that's true? Well, look. Well, because I say so? Well, look at it. We know what cosine alpha is, right? Cosine alpha is this, right? Cosine beta is that. So what's cosine of gamma? I always write y when I do it. It's not y. What is cosine gamma? It's A3 over what? The magnitude of A3. So if you square each of these things and add them together, what do you end up with? You end up with A1 squared plus A2 squared plus A3 squared. And what's under each of these? Squared. Thank you. What's under each of them? The magnitude of A squared over what? Over the magnitude of A. Well, here's the thing. You add those all, it's the same, it's the denominator, right? A1 squared plus A2 squared plus A3 squared all over of that squared. What is that numerator? Well, that is the magnitude squared. This is the magnitude squared. How do you find the magnitude of a vector? You square each component and take the square root, right?
Yeah, you wrote a 3 again.
Oh, I wrote a 3 again? Sorry. But do you see why that, so now do you see why that's true?
Yeah.
Okay. So then another thing we know right here is that 1 over A over the magnitude of A is going to be equal to cosine alpha, cosine beta, cosine y. You can figure that out yourself if you'd like. Okay. Vector projection. So you have that vector B, the blue vector on the left, and you have the vector Q, which is the orange vector. The projection of vector B onto A is notarized PROJ sub A B. So the projection of B onto A, and that vector is actually that red vector that goes from P to S. If you drop the if you drop the altitude essentially and connect from the initial point P to that point S, you get the projection. Can it go in the other direction? Could angle B go backwards essentially? Absolutely. Both of those are projections. The vector projection of B onto A. Again, this is something, you know, when I showed you dot product, at first dot product was just a scalar, but do we have something useful we can do with dot products? Yes. Dot products are integral to finding out the angle between vectors. Here's something else that seems kind of arbitrary and irrelevant, but is it going to have a use eventually? Yes, it'll have a use eventually. You knew that this angle right here, if we call that theta, that's the angle between. What is the cosine of theta equal to? What's the cosine of theta equal to? The magnitude of the P. If you want to find the cosine, what is it's adjacent over what? Adjacent over hypotenuse. So what's the adjacent vector here? Magnitude of PS over what? The magnitude of B. So what does that tell us? It tells us the magnitude of PS is equal to what? The magnitude of B times what? Which is exactly what's written right there. And in this case, what is PS? PS is the magnitude of PROJ sub A B. Like that. It's the same thing. Remember, what's the word that I said is the worst word to use in a math book? Do you remember what I said? Clearly or obviously. It's the worst word to use because either you get it or you don't and the book just insulted you, right? The book kind of does it unintentionally when it just says things like the projection, therefore it's the magnitude of B times cosine theta. You either see it or you don't. It's sometimes hard. It's sometimes very good to slow down for a second and just write that out. So we know from yesterday, our definition, it said that A dot B is equal to the magnitude of A times the magnitude of B times cosine theta, right? We're okay with that? That's from yesterday. What theorem do you use? What law do you use to prove that? Which we didn't prove, but what theorem would you use? You'd use the law of cosines, exactly. So let's rearrange this a little bit. What do we got here? We're going to rearrange. We're just grouping differently, right? But what is the magnitude of B times cosine theta? What did we say that was? Well, hold on. Let's start from the beginning. Yeah. What's the A? That's just the length of vector A, right?
Yeah.
And what is the magnitude of B times cosine? That's the scalar projection of B onto A, the comp B onto A, right? So what does that say? Well, you just write that out like that. Okay, that's nice. So how do we get to here? Well, let's rearrange a little bit. This is just the magnitude of A times the magnitude of B cosine is equal to A dot B. Nice.
Okay.
How did we get from here to here? Well, it's the same thing. We just pulled the dot down. This is just a constant. But what is A over the magnitude of A?
Cosine.
No.
You had the 3 cosines.
Yes, that's true. But what is A divided by its magnitude?
Oh, what?
It's just, what kind of vector does it become?
It's a unit vector.
It's the unit vector in the direction of
A.
What this means is that the component of B along A can be computed by taking the dot product of B with the unit vector in the direction A. The dot product of B times the unit vector in the direction A. So what that means is, if you ever want to find that scalar projection, you take B and what do you dot it by? The vector that goes along this direction that has a magnitude of 1. So if you have A, how do you do that? You find its magnitude and you divide by its magnitude. And then you just dot it by B. So if you do A over the magnitude of A dot B, what do you end up with? You end up with the magnitude of B times cosine, which is the scalar projection. It's a lot to take in. It just makes things a little simpler when you're actually finding things out.